Imagine standing beneath the night sky and watching a massive rocket suddenly transform the darkness into a bright wall of fire as it rises from Earth and begins carrying an entire fleet of satellites towards space. This is exactly the kind of technological achievement that has become increasingly common because of SpaceX's rapidly developing launch system. The latest confirmed SpaceX mission involved a Falcon 9 rocket launching a group of Starlink satellites into low Earth orbit, continuing SpaceX's ambitious mission to create one of the largest satellite networks ever built around our planet. At first glance, the launch may appear to be just another rocket launch, but behind those few minutes of spectacular fire and thunder lies an extremely complex operation involving advanced rocket engines, precise navigation systems, satellite technology, orbital mechanics, and one of the most important ideas in modern spaceflight, rocket reusability. The Falcon 9 does not simply rise into the sky and disappear forever. Instead, after completing a major part of its journey, its first stage separates from the upper stage and begins a carefully controlled return journey back toward Earth. This is what makes SpaceX's launch system so different from the traditional rockets of the past. While older rockets were usually discarded after a single mission, SpaceX designs its Falcon 9 boosters to launch, land, be inspected, refurbished, and launched again. Every successful mission, therefore, represents more than just another group of satellites entering orbit. It is also another test of whether humanity can make spaceflight more routine, reusable, and affordable. The mission began with a carefully planned countdown that involved hundreds of engineers, computers, tracking systems, and weather specialists monitoring every important condition. A Falcon 9 rocket standing vertically on the launch pad contains enormous amounts of highly refined rocket fuel and liquid oxygen, which must be loaded and managed with extreme precision. At the moment of liftoff, the rocket's Merlin engines produced an enormous amount of thrust, allowing the vehicle to overcome Earth's gravity and begin accelerating upward. During the first few minutes, the rocket passed through the thickest parts of Earth's atmosphere, where aerodynamic forces and intense vibration placed enormous stress on the vehicle. The Falcon 9 had to continuously adjust its trajectory using onboard computers and guidance systems to follow the precise path required for the mission. As the rocket climbed higher, the atmosphere gradually became thinner, and the vehicle continued accelerating to an incredible speed. Eventually, the first stage completed its primary job and separated from the second stage. The upper stage continued its journey with the Starlink satellites, while the first stage began one of the most dramatic parts of the mission, returning to Earth using a combination of engine burns, aerodynamic control surfaces, and precise navigation. The booster changed its trajectory and began descending through the atmosphere. At this point, the rocket was no longer simply falling. It was actively controlling its movement through space and air, preparing for a controlled landing on a drone ship positioned far away in the ocean. Of the most impressive technological aspects of the entire mission, after traveling thousands of kilometers per hour during its ascent, the first stage had to slow down and guide itself toward a relatively small landing platform floating in the middle of the ocean. During its descent, the booster experienced extreme heating as it re-entered the atmosphere at high speed. Small grid fins helped control its direction, while its engines performed carefully timed burns to reduce its speed. As the booster approached the drone ship, its landing lights deployed and the engines performed the final landing burn. In just a few seconds, a vehicle that had previously been traveling upward with enormous power had to transition into a controlled vertical landing. A successful landing means that one of the most expensive and technically complex parts of the rocket can potentially be used again for another mission. This reusability is one of the major reasons SpaceX has changed the global space industry. Instead of building a completely new rocket for every launch, the company can reuse certain boosters multiple times. This allows launch operations to become faster and potentially reduces the cost of sending payloads into orbit. The idea is simple in theory but incredibly difficult in practice because a rocket must survive the violent conditions of launch, the vacuum of space, the extreme heating of atmospheric re-entry, and the precision requirements of landing. Every successful recovery demonstrates that reusable orbital-class rockets are not merely an experiment but an increasingly important part of modern space transportation. While the first stage returned toward Earth, the Falcon 9's upper stage continued carrying the Starlink satellites into orbit. These satellites are designed to operate in low Earth orbit, much closer to our planet than traditional geostationary communication satellites. After reaching the correct orbital position, the satellites are released from the rocket in a carefully controlled deployment sequence. At first, they may appear to be traveling together as a group, but over time they use their own propulsion systems to gradually move into their designated positions within the Starlink constellation. Each satellite contains communication equipment designed to send and receive data from ground stations and user terminals. The overall goal is to create a huge network of satellites moving around Earth and providing internet connectivity to different regions. This technology could be especially useful in remote areas where installing traditional fiber optic cables or building large communication networks is difficult. Ships traveling across oceans, aircraft flying long distances, isolated communities, emergency response teams, and locations affected by natural disasters could all potentially benefit from satellite-based internet services. Unlike traditional internet systems that depend primarily on cables, towers, and ground infrastructure, a satellite constellation can provide connectivity from orbit. However, creating such a massive network also brings new challenges. Thousands of satellites must be carefully tracked to prevent collisions. Operators must coordinate orbital paths, and scientists must consider the effect of increasing numbers of spacecraft and debris in Earth's orbit. The latest SpaceX launch, therefore, represents something much bigger than a rocket simply carrying satellites into space. It demonstrates how quickly the relationship between humanity and Earth's orbit is changing. In the past, space launches were rare, extremely expensive, and often performed only for major scientific or government missions. Today, reusable rockets are making launches more frequent, while satellite constellations are transforming orbit into an increasingly active technological environment. Every Falcon 9 mission contributes to this new era by testing the limits of reusable hardware, improving launch efficiency, and expanding global satellite connectivity. At the same time, the growing number of spacecraft in orbit creates important questions about space traffic, orbital debris, astronomy, and the long-term future of Earth's space environment. If humanity continues launching satellites at an increasing rate, the need for responsible space management will become more important than ever. The most fascinating part is that this may only be the beginning. In the future, reusable rockets could launch more frequently. Larger satellite networks could connect more people around the world, and advanced spacecraft could transport humans and cargo to the moon and eventually Mars. What looks like a single Falcon 9 launch today could therefore be viewed by future generations as one small step in the transformation of space from a distant frontier into a busy and essential part of human civilization. The real question is no longer whether humanity can regularly reach space, but how far we are willing to go once reaching space becomes faster, cheaper, and more routine.